coming in from the sun. So the more molecules of CFC12 there are in the way of the photons coming in from the sun, the faster it's going to get destroyed. Yeah? This is going to be, well, first of all, this is going to be positive or negative, just make sure people are sort of with me. You put the CFC12 in, now you've left it, what's it's going to be overall? Negative, it's going to go down, okay? Minus some constant, yeah, times the concentration of CFC12. Very simple equation of how that gas behaves. Anybody know what the solution of this equation looks like? We've already talked about it before, we've seen this equation before. Well, just, you don't have to do any maths, just sort of think intuitively. If I was to sketch, again, you don't have to do maths in your in the papers here, but it helps to draw things so that you can sketch. You know, I think it really shows that you've understood something if you draw a quick sketch of how I think something's going to behave. Okay? You can do a lot with a figure like that. And first of all, rest assured that at least one of your examiners won't care if you don't get the sketch exactly right. Okay? And probably the other one won't either, I can't answer now. But so the point is, don't not put sketches in your scripts because you're worried that you might get the line in slightly the wrong place. Okay? You can demonstrate a lot of understanding with a sketch. And just looking at this figure, if I was to draw concentration of CFC12, also don't spend a lot of time on your sketches, because I mean, and again, it's just to show that they've got the basics here. If I was to draw time against the concentration of CFC12 after I've stopped emissions, okay, if I look at this equation, the rate of decline, it's going to start off going downwards, okay, so that's where it is to start with. And what's going to happen to the rate of decline? Somebody, yeah, that'll do, okay? It's going to look like that. Because the rate of decline is going to decline as the concentration declines. And somebody can probably tell me what the name of this curve is. It's an exponential, okay? But it doesn't, from your point of view, it doesn't matter that it's an exponential, it's just that, look, the rate of decline goes down as it goes down. Okay, but this rate of decline goes to zero only when the concentration's gone to zero. So this is going to carry on declining until the concentration's gone to zero. So CFC12 will all eventually disappear, which is what's happening here. So that's a sort of, if you like, a typical greenhouse gas. We say typical because most of the gases behave like this, but of course the big exception is CO2, and we're going to talk about why now. But so most greenhouse gases you can characterize with a lifetime. You can say it's gone, and CFC12 is about a 200-year, or I can't remember exactly what the number is, 100 and something year lifetime in the atmosphere. Methane has a lifetime of about 10 years. HCFCs, the various HFCs have lifetimes of the order of 10 years. So most greenhouse gases, they get destroyed by something, completely destroyed, sent away into, so concentrations go to zero, so you can characterize them as having a lifetime. What about this grey band here? This is what happens to CO2 after I pump it into the atmosphere. So I put a slug of carbon dioxide into the atmosphere, and then I watch to see what happens to its concentrations. And they fall rapidly to start with, and then they just sort of stop falling. They're still going down very, very slowly. And this is 800 years here. So there's still an awful lot of it in the atmosphere after 800 years. Why is that? You've got to ask ourselves, why is that the case when we have, in the carbon cycle, this massive carbon pool in the ocean? And I've also told you that over hundreds of years, the ocean turns over. This isn't something we can answer by just saying, oh, the ocean's a bit slow. Because, on multi-century timescales, the ocean does communicate with the atmosphere, it does turn over. So it's not just a matter of timescales here. There's something else going on. Can you all see why there's a puzzle here? Why we've got something to explain. So what's happening is a very simple piece of ocean chemistry, which is, and hopefully you've all done chemistry at least to a level that you know what a buffer solution is. What's the idea of a buffer solution? Okay? Probably looking a bit worried. You did tell me about that once, but thankfully forgotten all about it. So I brought one with me because I thought you might need reminding. And I might need a volunteer, but I'm probably not allowed to ask you to taste things. But it is just, I can show you what I've, anyway, I'll tell you about it, let's see if anybody wants to. So in the ocean, we've got, obviously there's a lot of salt, there's also a lot of dissolved carbon, and it's in three forms. It's in the form of dissolved CO2, in the form of bicarbonate, that HCO3 minus ion, and in the form of carbonate, that CO3 2 minus ion. Okay? And if you wait for long enough, and the ocean's all stirred up and so on, these are in equilibrium. And so there's a certain natural ratio between the concentration of CO2 and the concentration of bicarbonate, and the concentration of bicarbonate and the concentration of carbonate. And those natural ratios are 1 for CO2, 175 for the bicarbonate, and 21 for the carbonate. Okay, so most of it's in the form of bicarbonate. So, if we dissolve CO2 into the ocean, we get a reaction. We should have written on this slide, actually. But somebody who can remember their... Anybody remember enough GCSE chemistry to tell me what happens when I dissolve CO2 into seawater, or just water? CO2 plus H2O. Now, it's one of these reactions which is reversible, so I'm going to do one of these little signs, okay, because there's an equilibrium here. And what am I going to write down here? So, I'm making this up as I go along, but one of these things is HCO3 minus, and the other one must be an H plus. So I've got everything sort of balanced here. Yeah, that'll do. Alright? So let me sort of see how, and then there's another equation which is HCO3 minus plus H2O. Again, it's reversible. Is another it's CO3 2 minus. I can make H2O on the wrong side, haven't I? If I've got that sort of minus, that's must be an H plus. No, hang on, I didn't need the H2O for this one. I think there's no problem. Yeah. Yeah, so there's another equilibrium reaction between that and the bicarbonate. Okay? So those are the equations we're talking about. These are reversible reactions. Yeah? Ringing some bells, I hope. Okay, you don't need to write too much about the details here. The bottom line is you've got these three species which are in equilibrium with each other. And so I brought some with me. Okay, so this is straight water, and this is a solution of bicarbonate of soda, exactly the same stuff, bicarbonate that exists in seawater. And if you put CO2, if you dissolve CO2 into the water, you liberate H plus ions. What does that mean to the water? It makes it more acidic, okay? Strictly speaking, it makes it less alkaline if you're talking about seawater. People talk a lot about the acidification of the oceans. what they probably should say is the dealkalinification of the oceans, but it takes a bit longer to say. Okay? So oceans are slightly alkaline naturally, and they should be slightly alkaline. In fact, all the life in the ocean is used to it being ever so slightly alkaline, and so they're being essentially neutralized by the solution of CO2. All right, but anyway, that's an aside. So we could simulate this by bubbling CO2 through here. It would take a long time. So I brought some lemon juice with me. So securities around. I tried that last. So if I put the same one. Oh, damn it. No, I lost track of how much I put in. But so if I try and well, okay, so I've kind of messed up the experiment because I can't get the same amount here. If it was the same amount, okay, we'll try harder next year. Okay, then if you taste these two, what do you expect to taste? Given that this bicarbonate is a buffer. Okay? So the one with the lemon juice will taste sour, and the other one won't. Okay? And if anybody wants to confirm this is true, these are nice clean glasses. Anybody want to confirm this is true? But I'm probably not allowed to ask you to do that, but or do you want me to drink them for you? Then you'll just have to take my word for it. So we're kind of stuck here. But you can try it afterwards if you want to. Bicarbonate of soda and lemon juice. Okay? You can't be intrigued, can you? No? Not intrigued. No? No?
I'll agree.
Useless not. Go on, come on now. Confirm the same. Okay?
This one first.
On whichever. Yeah? I've no idea whether I've enough for it to even be tastable, but okay.
So there's a hint of lemon.
Okay, there's a hint of lemon. It just tastes weird because it's consumable. Okay, but the point is, it didn't taste sour. Yeah, and if we had a litmus paper, we could put a litmus paper. Thank you very much. It's a nice Don't go with poison. No, I wasn't about that. It's all brilliant. Okay. I want you to remember this. You'll remember that. You won't remember this slide. Okay? Because it's really important. And it's also a little bit, the sort of consequences of this are a little bit complicated. If we increase the amount of carbon in the ocean, you can't just make the ocean positively charged. You can't just increase the amount of H+ ions in the oceans indefinitely, okay? Because alkalinity, overall the alkalinity is conserved. I mean, it's getting slightly more neutral, but broadly speaking, the pH of the ocean doesn't change much, okay? Because it's a buffer, because it's got this property that you've got these naturally occurring species that keep the concentration of H+ ions, to keep the pH of the oceans more or less constant. So, if we increase the total amount of carbon in the oceans, the fraction of that carbon that's stored as carbonate has to go down, because we have to basically keep the amount of charge in the ocean the same. Because this has got, every carbon atom here has two, there's a double negative charge on it. Yeah? Every carbon atom here has a single negative charge. So if we increase the total amount of carbon atoms, we want to keep the total charge the same, we've got to have more of it in this form. Does that make sense to everybody? Yeah? So what happens is, as we increase the total amount of carbon in the ocean by dissolving CO2, there's a natural shift from the bicarbonate form to the carbonate form of the carbon in the oceans. So the ratio, the fraction of ocean carbon which is stored as carbonate goes down. And this is how a buffer works. This is the working of the buffer. This is what the buffer solution is doing. It's adjusting the amount you've got in these different pools in order to keep the overall alkalinity of the solution the same. That's how buffer solution can work. There's always two forms of something in a buffer, and they're in equilibrium, and as you try and make it more acid, they sort of fight against you. That's how buffers work. Okay, now, 10% of the dissolved inorganic carbon is in this form of CO3, this is in this carbonate form. So if we add a ton of CO2, a ton of carbon in the form of CO2 to the oceans, we have to convert, the oceans have to convert a ton of bicarbonate into a ton of carbonate, a ton of carbonate into a ton of bicarbonate, and so 100% increase in the concentration of CO2 comes back into equilibrium with a roughly 10% increase in total dissolved inorganic carbon. Remembering that the fraction of dissolved inorganic carbon which is in the form of CO2 is very small. So you don't really need to worry about the actual CO2 in the ocean, it's what these other forms of carbon do and CO2 is always in equilibrium with them. So if you know the concentration of HCO3 minus, then you know the concentration of CO2, because the alkalinity is always the same. Right? So what happens is that basically, as you put more carbon into the ocean, you increase the concentration of bicarbonate, which opposes the solution of CO2, if you like. It means that the concentration of CO2, the natural concentration of CO2 in the ocean goes up. So instead of that CO2 dissipating away, there's this sort of resistance coming out of the buffering in the ocean. And so you're trying to make the ocean more acidic by adding CO2, but the ocean is fighting against that. Think of it that way. So if we dissolve carbon in the oceans in the form of CO2, crucially, the sort of bottom line here, the equilibrium concentration of CO2 in the oceans increases roughly 10 times faster than you would expect it to increase if there were no buffering. Okay? So, for example, going back to those glasses, okay, when you just add lemon juice to plain water, the concentration of lemon juice went up, the sort of the stuff you could taste, went up linearly with the amount of lemon juice you put in. So it tasted acidic. But when we added it into the buffer solution, it couldn't go up. It was held. It was held back, so you couldn't taste it. Okay, so it's as if the buffer is resisting absorption of that lemon juice. One way of thinking about it. Yeah, okay, you can see clearly. I'm trying to sort of give different analogies for how this works. But the bottom line is that because of this natural ratio between carbonate and bicarbonate, because of this process whereby the carbonates convert to bicarbonate as you dissolve CO2 into the oceans, the equilibrium concentration of CO2 goes up much faster than you'd expect if it was just a simple solution process. That's sort of the best way of just remembering what goes on. And as a result, I pointed out at the beginning, you've got this atmosphere carbon pool of about 600 billion tons of carbon. I'm going to use that notation GTC quite a bit, but the capital G stands for giga tons. Yeah? And the oceans, they contain almost 40,000 gigatons of carbon in the form of dissolved in organic carbon, but the concentration of CO2 in the oceans goes up 10 times faster than you expect because of this buffering process. And as a result, you can think of it, this is a reasonable analogy for how it's working. You've got an effective ocean pool of carbon, which is 10 times smaller. Think of the ocean as a big basin with a diameter, with an area 10 square meters, okay? But we're saying, actually, so and we're pouring water into this basin. It's going to rise very slowly. But if we have some process which means the water rises 10 times faster than we expect, another way of thinking of that is the basin's 10 times smaller. Yeah? So it'll go up 10 times faster. And so you could think of this in terms of the effective ocean pool is only, well, around 4,000, not 40,000 billion tonnes. Do you see where I'm So the point is, if we put, say, 600 gigatons of carbon into the atmosphere, so that's sort of enough for an instantaneous doubling, okay, so we just put, overnight we put the same amount of carbon dioxide into the atmosphere as is there already, and then just leave it, it'll sort of equilibrate through the atmosphere-ocean system. Most of the carbon in the system is in the oceans, but you won't have it going down to 600 over 40,000, which would be a very small number. It'll go down to only roughly 1/6. You see, that's about 600 over 38,000. Okay? So 1/6, 10 to 20% of the carbon we dump into the atmosphere stays there forever. That's another way of thinking of it. You need to be a bit careful how you put this, because of course it's not the same carbon, it's not the same molecules. It all gets mixed through the carbon cycle. But in effect, that's what that in effect means, yeah? In effect, 10 to 20% of it stays there in the atmosphere. Yeah? And of course this has very profound implications, because it means that defossilizing carbon has a permanent effect on the climate system. It's not like, say, the impact of the impact of a temporary change in albedo as a result of other forms of industrial pollution, for example, which might have a temporary cooling effect on the climate system. If you switch that off, if you switch off that pollution, then because the Earth is exchanging energy with space, and there's in effect an infinite amount of space, the system will go back to exactly where it was before. So when we were talking about the way the temperature system responded, we talked about, doubling CO2 and then coming to a new equilibrium, and then if you switch the CO2 back down again to pre-industrial and waited long enough, it took quite a long time, but if you waited long enough, temperatures would go back down to what they were before. That's what happens with temperature. Because joules, if you think of sort of like if you think of the joules as like molecules of carbon, joules can go off into space or be absorbed from the sun indefinitely. There's a sort of an infinite pool of energy out there for the Earth to exchange energy with. But there's not an infinite pool of carbon. In fact, the carbon pool is quite, although it looks like it's effectively infinite because it's so big in the oceans, because there's so much carbon there, and because of this little piece of ocean chemistry that we've just tried to demonstrate, the actual carbon pool is quite small. Yeah? So, for example, if we were to burn all of this fossil carbon, and we're more than capable of doing so, and that estimate is probably too low, it's probably more like 4 trillion. I mean, we keep finding more exotic forms of fossil carbon and working out how to mine them, so I mean, who knows really what the exploitable fossil carbon reserve is. But if we were to burn all of that, you're essentially putting not 10% of the active carbon in the active cycle, you're effectively doubling the amount of carbon in the active carbon cycle. And so that doesn't mean that what you get would be, if you did that, you'd get CO2 concentration in the atmosphere going up way higher than doubling to start with, but then coming back down to a level that was about double what they were before. And then staying there. Because the only process which reconverts this carbon, which you put into the active carbon cycle. The only process which takes it back out of the active carbon cycle is refossilization, if you like. It's got to be turned back into rocks. And that's a pretty slow process, millions of years. So, taking fossil carbon and dumping it into the atmosphere is an irreversible process. And that has quite important implications. Because a lot of the discussion of CO2 policy is around aiming to get emissions down by 50% by 2050. And you know, the UK carbon policy is all about our contribution to this, getting our own emissions down 80% by 2050. But that's justified in terms of an overall global target of getting emissions down by 50% by 2050. I'll be talking more about this at 12 in the environmental geography lectures. But the problem is that if defossilizing carbon has a permanent impact on the carbon cycle, what do you have to get emissions to in order to stop the climate changing? Zero, okay? Because it lasts forever. So, as a good way of sort of reminding you what this, let's just ask ourselves, if I've got a gas, think of we do. Right out CFC 12. I'll call it a generic CFC, okay? If dCFC by d time is equal to minus K CFC, concentration of CFC, then if I raise the concentrations of that CFC in the atmosphere, and I want to stop them rising, then I can choose an emission rate, okay, which is equal to, if I choose an emission rate for CFCs, which is equal to K CFC times the concentration of CFC. So that's the destruction, that's the emission, concentration is going to become stable. So if my gas has a natural lifetime, there's always an equilibrium rate of emission. But if, like CO2, the gas effectively has no lifetime, or an infinite lifetime, then there is no safe emission rate. So another consequence of this, there's a big, a few years ago there was a lot of enthusiasm for a program called Contraction and Convergence, the idea that we would aim for 1 gigaton per person per year rate of emission, which is sort of somewhere between Chinese and Indian rate of emission at the moment, I think it is. And that, if we could get to this, the problem would be solved. And there were some arguments about how we would get there and how it should be divided up when we get there. The point is, that's not a solution, because it means you're still emitting carbon, and the absolute carbon climate is still changing. So, and the danger with this focus on the short term, and this we will take through to topics for the environmental geography lecture, is that it focuses your attention on technologies that might help you get down by the first 50%, but won't necessarily help you get over the next 50%. So the technologies you'll need to get emissions to zero are not those you need to reduce them by 20%. Efficiency, for example, putting in low energy light bulbs might reduce emissions by 10 or 20%. But it can't reduce emissions to zero. Doing things more efficiently, by definition, can't get you to zero. And this is actually a big problem in policy at the moment, because people are focused on getting emissions down in the short term, and the technologies which we need to get emissions to zero are by and large the more expensive ones. They're dominated by carbon capture and storage. The only way effectively to get emissions to zero is by large-scale carbon capture and storage. That's expensive, it's an expensive way of changing the emissions in the short term, so it's just not being invested in. So nothing's happening on carbon capture. Nothing's projected to happen until we get to 2030, 2040, by which time it will be too late. So it's a simple piece of ocean chemistry with pretty profound implications for policy. Let's talk about, quantifying its implications. So this is a study we did a couple of years ago, which is sort of crudely summed up as thinking about the fate of the trillionth ton of carbon. So what this was about was we were generating large numbers of idealized emission scenarios. We varied the year at which we started to turn emissions around, and the rate at which they went down, and those kinds of things. So we generated lots and lots of different emission scenarios. And then we looked at the response using a simple coupled climate carbon cycle model. And I can show you the equations of the model, but you don't need to worry about them. You certainly don't need to remember them. But you should have already captured broadly the principles behind the model. And that's what I've been trying to do in these lectures. You don't need to remember the equations, but you should see where the equations come from. You should sort of see why they make sense. And this is essentially what the model consists of. It's a sort of set of concentric pools of carbon, where this is the atmosphere pool. Think of these as cylinders in a big basin. Okay, so there's the outer basin, which is the ocean. It's 10 times smaller than you think it might be if you look at the size of the carbon pool. We've already talked about that. The outer basin, which is the ocean. We've got an inner basin, which is sort of the near-surface ocean, and then we've got a middle basin, which is the atmosphere and mixed air, which is where the carbon goes straight away. Okay. So you're pouring the carbon into the atmosphere, and it's flowing out of there into the atmosphere near-surface ocean, into the near-surface ocean pool, and then it's flowing out from there into the deep ocean pool. You see, in principle, what's going on here, and that therefore the level at any given time is given by just adding up the level in the deep ocean pool, the excess level in this intermediate pool, and the excess level in the atmosphere mixed air. It's a very simple way of representing the carbon cycle. The reason it's justifiable, those are the equations, but don't worry about them. They probably look quite familiar to you, because they are very similar to the equations we use for modeling the climate system. The way we can justify it is by saying, thinking of the carbon cycle in that way gives you behaviour that looks like this. So, we can mimic the behaviour of much more complicated carbon cycle models using this really simple conceptual model. There's one other. So those are the three equations. That's sort of the accumulation of CO2 in the big ocean pool. There's the fact that ocean sort of only slowly gets down into the deep ocean, so we have a bit of a constraint here. And then we have the fact that the carbon is only slowly taken down into the deep ocean, and then it's more rapidly taken down into the near-surface ocean. Again, this is just telling you what the equations are, but you can think of these as just ways of representing the sort of intuitive behaviour you'd expect from that system of concentric cylinders. If you like, you don't need these equations. You can actually build a carbon cycle model by just, by building a set of cylinders and with holes, with particular size holes between each one, pouring water in and using that to predict how the carbon cycle will behave. So in fact, a while ago, this is kind of the way people did computing. You sort of build a fluid computer. Maybe a good demo. So you don't need to solve these equations on a computer. It's a lot more convenient to do it that way than it is to do it by pouring water around. There's one more term in here which is important, which is, as we warm up the climate system, as temperature rises above this equilibrium level, which is the temperature with which the carbon cycle is in equilibrium. And that's, we sort of, in this model, we assume that sort of everything alive at the moment is pretty much used to carbon dioxide the temperatures that are typical over the past couple of hundred years. So that's not necessarily the same as the very long-term equilibrium temperature, but it's just the average temperature over the past century or so. If you warm the system up, many processes kick in which result in the release of more carbon. For example, if I were to warm up if I was to warm up that solution of bicarbonate, I'd see it eventually fizz. I mean, you release carbon dioxide. If you warm up the oceans, they expel carbon dioxide, or at least they don't take up as much carbon dioxide as they would do otherwise. So that's one process, that's one feedback process. Another, much more important one actually, is as you warm up soils, you change the way soil microbes work, you speed up soil microbes, they respire faster, and they release CO2 through respiration. So we get an additional emission of carbon, which is proportional to how high temperatures are above what they've been over the past 100 years or so. This is a feedback term. And this is important because it means that as the system warms, you actually add more carbon into you add more carbon into the atmosphere, and that actually causes further warming because it's a positive feedback. It's also pretty contentious, the size of this term. It's present in most carbon cycle models, but how big it is very much dependent on how you model it. In fact, there was a paper published only a few weeks ago by Peter Cox and co-workers. Peter Cox is somebody who really made his name in the sort of around the turn of the millennium by pointing out that a warming world could cause the Amazon to die, and that would release a huge amount of carbon into the atmosphere. So that would be very strong positive feedback in this term. And they just published a paper a few weeks ago saying, looking at observations of the Amazon, they actually reckon this effect isn't nearly as big as they thought it might be. But you know, it's kind of part of the science where results seem to flop around by a factor of 10 as you go sort of from year to year. So there's a lot of uncertainty in how the biosphere is going to respond to rising temperatures. Part of the problem, of course, is we don't really see, we're not, you can look at ocean chemistry and do experiments on it, but you can't really do experiments on the Amazon. I mean, there's a lot of stuff happening in the Amazon, so it's very hard to tease out what's the response to rising temperatures versus what's the response to changing land use practices, deforestation, and the rest of it. We don't just run this model, we constrain it. You have to use, when we're using simple models like this, you need to match things you can observe, because you can't just take all the parameters, you can't just use the sort of basic physics argument to say what the model parameters should be. So we put in these various constraints on the model, and all this, by the way, is available on the WebLearn site. So you can download this model. In fact, you can download a more sophisticated version of this model, which has all the other greenhouse gases in it as well. You go to the WebLearn site, you'll find SCM_MPP that we put together for the Masters in Public Policy program. That's the simplest version of the model. Don't tell the Masters in Public Policy students. But so the simplest used version of the model is the one designed for the Masters in Public Policy students. And there's a little sort of set of questions I think you might want to play with that. I had hoped to devote one of these lectures sort of a class working with that model, but we've spent a bit more time on teaching themselves, so we haven't really had time to do that. So I'm afraid that's probably not going to be possible this year. On the other hand, if people are interested in using it to illustrate, for example, extended essays you do on the basis of this option, then you can just come and talk to me, it's all there, there's all those sort of suggested exercises you can do with it. And the Masters in Public Policy students seem to manage to do it, so I'm sure you guys will be able to. It's all there in Excel, it's reasonably straightforward. So do have a look at it. And the sort of suggested things you can do with it is to play around. If you can vary the sensitivity of the model, look to see how it responds. You can vary the ocean diffusivity, vary the sort of rate at which the ocean takes up either heat or carbon. You can see what happens when you try negative emissions, how much do you need to suck out of the atmosphere to hold temperatures down, and play around assorted solar radiation management, assorted geoengineering scenarios. That's all, so you can explore with this as well. But what we did was to look at lots of different scenarios like this, various scenarios of CO2 emissions going up, coming down again, and the sort of key observation, which, arguably, you could say was obvious from the start, in the sense that if carbon dioxide lasts forever, what matters is the total amount you dump into the atmosphere. It doesn't make any difference whether you dump it fast or slow. And that's indeed what comes out of the model. The temperatures you reach in 2150 or something are pretty much the same, regardless of whether you follow the blue trajectory, which has a lot of carbon dioxide being injected rapidly and then emissions falling very fast. So the area under the curve is the same. So this blue area is the same as that one. So the area under the blue curve, the red curve, and the green curve are all the same, meaning the total amount of carbon dumped into the atmosphere is the same in all these three scenarios, and the temperature response is the same. So what determines the temperature response, and indeed the risk of dangerous climate change, is the accumulation of carbon dioxide, the total cumulative carbon dioxide dumped into the atmosphere. And of course this has all sorts of implications for mitigation policy, which we'll talk about in the environmental geography lecture. But the key point is that worrying about emissions when the emissions peak occurs, or what emissions are in 2020, is irrelevant if you don't also think about how you're going to manage the total cumulative amount of emissions. This is how peak CO2-induced warming relates to cumulative CO2 emissions. And to put this in context, that's emissions to date. So we've released roughly 500 billion tonnes of carbon so far. If we burn all the oil and gas, that will take us to about 1 trillion tonnes, which would be equivalent to that, which would give about 2 degrees of warming. If we burn existing oil, gas and coal, that takes us to about 3.5 trillion tonnes, which is plenty enough to take us up to 4 degrees plus. And of course there's unconventional reserves there as well. So one of the implications of this is that you ask yourself, what does, we talked about how the timing of the emission peak is irrelevant if you think about the total, if you fix the total. So when this paper came out, there was a lot of complaint about that it might send a very bad message that sort of implies it doesn't really matter what you do now. And therefore it might give people the impression that policies now don't make any difference to the risk of dangerous climate change. You can see why that's a way of spinning this particular observation. And so one way of thinking about that question is to ask, well, what happens if you decide you're going to aim for 2 degrees, and so if we want to aim for 2 degrees, that means we're going to limit total injection of carbon dioxide into the atmosphere to roughly 1 trillion tonnes. Okay. That means by deciding to aim for 2 degrees, we've decided already, somehow, that emissions will decline on average at 2.5% per year from now on. So, in other words, emissions, they're not declining at 2.5%, they're still going up. But the point is that by deciding to go to 2 degrees, you basically decide you're going to have a trajectory which, on average, follows this line. If you go above it to start with, you've got to go below it later. Yeah? So, if you ask about, so what's the impact of delaying the time at which you start emission reductions? Well, that's really given by the additional area under the curves. Remember, it's the area under these curves that matter. So, if I delay 12 years or so, I add and then go down at the same rate, I'll add an additional enough additional carbon into the atmosphere that I get an additional 0.4 degrees of warming. Another 200. So the area, this yellow area here, is going to be 200 billion tons. Yep, I think that's right. I'm doing it in my head, but you can check it. Yeah? So each of these areas is another 200 billion tons. And so if you're thinking about the implications of delay, then that's how fast the temperatures we're committed to go up as you delay starting your emissions reductions. One interesting consequence of this, of course, is if you decide that if you resign yourself to the fact we're going to 3 degrees anyway, that implies our commitment is actually less onerous. We only need to reduce it 1% a year from now on average. We still have to reduce. Unless you reduce emissions, you're not going to stabilise temperature. And the rate at which the temperature we're committed to goes up faster, because these areas are also an additional 200 billion tons, but there, because it's been flattened out, the areas, the distance here is less, the time is less. You see how that area is the same as that area. Look, these areas go on out forever. Can you believe that the dark orange area there is the same as the yellow area there? It's just been flattened out. Yeah? So it means that because the area is what determines the warming, the committed warming from following this trajectory is 0.4 degrees higher than the committed warming following this trajectory, which means your committed warming, if you accept that you're going to reach 3 degrees, then your committed warming is going up by 0.4 degrees in only 8 years or so, a shorter time. And if you decide you're going to go 4 degrees, it's going up even faster. You see how? Okay? So that's sort of about CO2. Another big issue at the moment in climate policy is non-CO2 warming caused by other factors, not CO2. And these are often discussed in the literature as short-lived climate pollutants. So the big ones we talk about are methane and black carbon. These are big pollutants which have a major impact on the climate. Methane, I think you're probably all familiar with. Sources of methane are primarily enteric fermentation in livestock, so cattle burping actually